I can see Professor Patnaik now.
Yes, sir.
Yes, sir. We are live now. Please start.
Sir, you please speak, sir. So, good morning to all of you and good morning to all the participants.
I can see Professor Patnaik now.
Yes, sir. Professor Ramamurthi, sir, you can maybe
yes, sir. We are
address
live
the
now. Please
participants. Yes, sir. Sir, you please.
Yes. Professor Patnaik, my two teaching assistants, Nikhil Chitnavis and Leti Chanakya, and also the participants. Good to see you on this live question and answer session in the course on safety, explosions and explosion safety. I hope you are enjoying the course. You know, the course is basically simple, but at now and then all of us do get stuck up here and there. If you have any questions, I think it is the right time to answer your questions. We have been answering your questions on the portal, and some of your questions are extremely pointed and sharp and very good questions. Like you are talking about how do you apply the acoustics theory for shock reflection. Again, the results of acoustic theory and shock reflection theory do not match. Why is it so? We have answered some of your questions, and also other questions also are extremely pertinent. Like you asked about the different processes involved. Of course, you know, we do get to a little bit of thermodynamics now and then, but thermodynamics is the basis of all life engineering innovations, and therefore its session is necessary. If there are any specific questions, I think we would like to answer you. If not, we will go back to the assignments and try to answer some more of the
Sir,
assignment. What yes, now and then. Yes, please
sir,
go ahead.
there is one Shashank Shekhar. He has asked a very interesting question and very, he is a specialist from the oil and gas industry. And he has a specific question. Maybe I'll read out the question, sir. He sent this question today morning. Under what condition a sound wave becomes a blast wave? That's the question one. And how come the ultrasound, especially he is referring to sonography, is not painful while sound wave is passing through different mediums? As per theory, of course, he puts in parenthesis saying my understanding, as per my understanding, it must be creating stress in the muscle as the blast wave creates in a steel column. When a blast wave gets reflected back from the rarer medium, a medium of low impedance. How is it that it's not painful for the the tissues of the body kind of thing? And how do we improve our understanding of thermodynamics? Any basic book that you want to recommend? These are the three questions, sir.
Okay. Thermodynamics is quite simple. I'll take your question, the last one first. You just deal with the three laws of thermodynamics. Law one, energy is conserved. Law two, there are certain situations in which you cannot get work done. Like what happens is you cannot. Also, other questions also are extremely pertinent. Like spontaneously like to assignments, and that is the second law. And of course, you have the third law, which is the datum. This is all what thermodynamics. What yes. Yes, please use. For board, of course, don't bother too much about thermodynamics. Maybe you take a primary book on thermodynamics which deals with systems, and the thermodynamics is the basis of also thermodynamics. I'm sure you know about it. Now, getting back to your question on sound, if there are any specific questions, yeah, and blast wave. How does a sound wave get converted to a blast wave? You remember in the first lecture itself, we talked in terms of a sound wave. It has very small amplitude. That means it's hardly any disturbance is there. And since there's hardly any disturbance, it's sort of reversible. It could go either way, left or right or up and down. Therefore, it doesn't really matter. It has no direction. Therefore, since it's reversible and the magnitude of the amplitude is so small that there's hardly any heat, it's adiabatic. We call it as reversible adiabatic or isentropic. Therefore, whenever sound wave travels in a medium, and adiabatic because the amplitudes are very small. what would happen if the amplitude increases? If the amplitude increases, you have a peak or a crest of the wave wherein the pressure is higher. When pressure is higher, automatically the temperature tends to be higher, and therefore the velocity at the crest is a little bit higher than otherwise. Therefore, that point moves a little faster, and therefore, instead of having a nice wave which is sort of sinusoidal, you have something like a steep fronted wave, and this steep fronted wave becomes more and more steep until it becomes a shock wave. A shock wave is a wave in which there is an abrupt change in properties because it is very steep. We call it as a shock wave. But this shock wave is driven. Therefore, when it propagates, the shock wave keeps decaying. It loses its energy. When it loses its energy, it becomes a little weaker. When it becomes weaker, the properties behind it are decaying down, and therefore what happens is you have a wind associated with the decaying shock wave. The decaying shock wave is what we call as a blast wave. And since the properties behind a decaying shock wave are changing, like the pressure is decreasing as it propagates, and a decreasing pressure, causes right? The wind to flow, or you have a wind, or you have a momentum, and that is what you have an impulse. Therefore, a blast wave is a decaying shock wave, and it is caused because of large amplitude motion. And in this particular course, we try to find out. Yes, please go ahead. Yeah. What causes this large amplitude motion? What causes the blast wave? And this is precisely what we are doing. Therefore, you find we are trying to figure out how much energy is released in some process and whether a blast wave gets formed. If a blast wave is not getting formed, is there some other form of an explosion which takes place, which could again cause some damage? And that's what we are doing. But in a nutshell, a blast wave is a decaying shock wave. Okay. A decaying shock wave is something which is caused. Okay. Because thermodynamics is quite simple. Shock wave, if it is not supported, keeps decreasing its amplitude or you just deal with the three laws of thermodynamics, the magnitude of the pressure behind it. This is to answer your question or the third question, namely, you're asking ultrasonic waves, sound waves, if it is reflected from a medium in which the impedance is lower than the impedance of the medium before. Won't an ultrasonic wave cause the same change? No, the question is, you cannot, we're talking of shock waves, we are talking of finite amplitude waves. Therefore, if I talk in terms of very minute amplitude waves, well, you cannot have these changes take place. And that is why you need something like a transfer, at least a minimum, a weak amplitude blast wave to be able to cause the I could answer your question. Is it okay? Are you there by any chance? Or
Sir, I can
Yeah.
read out some of the questions from the chat, sir. Some students have, some participants were asking. Especially, I think they're also a little worried about how do we prepare for the exam, and these kind of very very generic questions related to how to approach the assignments, and then specifics with reference to the assignments also. Maybe how to prepare for the exam is one thing I think looks to be a very overall general concern. And maybe I'll take up a technical question. Maybe that also you can address indirectly. One, I think it is Jairam Reddy. He's asking, something to do with real field scenarios. He's, oh my God, this is a very general, happiness of expression or something like that. But the question is, there is one Ravinder Singh. He's saying there was one question in which we have to find out reflected pressure of shock wave. It was related to the equation given by Kinney and Graham. Please elaborate on this.
Okay.
I'm not sure in what context or specific question he's referring.
Question. In fact, his question was, in the Kinney's book, derives an expression for the reflected shock pressure in terms of the incident shock pressure. And it gives in terms of gamma values that spontaneously transfer heat from lower incident shock pressure. Whereas in the course, what we did was, we calculated, we didn't therefore want to use the formula as such, and therefore we started from first principles. We calculated what is the pressure is behind the incident shock wave. When the shock gets reflected from a rigid body, it is rigid, therefore it reflects back with the same velocity. We could therefore calculate the pressure behind surging. When it loses energy, what happens is you have a wind associated with a decaying shock wave. And since this decaying shock wave is what we call as a blast wave. If you use formula from first answer, there is no reason why it should be different unless the gamma values which you use are different. The gamma we use for air is 1.4, and therefore the shower of blast process is reversed. And in this, the magnitude what causes this large amplitude wave motion. Therefore, you call it as released in some process. And I don't like too much to use the ready-made formula because we don't understand. See, this course is basically to understand more about the phenomenon process that takes place rather than to use any formula. Even for your final examination, don't learn, or for any examination for that matter, or even for your assignments, don't learn any formula. Just try to do the problem from first principles. If a formula is required, like you have the pressure behind a shock wave, or density ratio behind a shock wave is equal to gamma plus 1 divided by gus 1 2 over Mach number square, and that's what we are doing. It's a decaying shock wave, and a wave, well, if it is not supportive of the pressure behind it. Waves, even if it is reflected from impedance of the medium before. Therefore, we would like you all to do the problem, and this is the way I think. That question was, for the reflected shock pressure in terms of gamma, you have a peak or a shock pressure. Whereas in the course, what we did was, and therefore we started when the shock gets reflected from a rigid body, therefore calculate the pressure otherwise with the pressure behind the incident shock law, or we do which is sort of sinusoidal.
Sir, your
in which there is a abrupt is very steep. We call it as a shock. The shock wave
sir,
is peaking. It becomes weaker. The last wave is a dealing for your assignments. Don't learn any formula. Just try its amplitude. Yeah, like you have the pressure. You're asking ultras is equal to gamma plus, in which the impedance. What are the UPS system, and therefore memorizing of them is a little beyond. Is that a problem?
Sir, there seems to be some problem, sir. There is an echo coming. I'm not sure whether NPTEL is also, Swayam is also showing the YouTube video parallelly. That can be a
Sir,
source of...
if anyone is playing the YouTube video, you should mute that audio. Will come back.
Yeah. I think that people have to switch off. All of us locally. I think there is a bit of, it's more like a reflected shock wave, similar to that. There is an reflected YouTube with a time delay coming back. So some participants have been pointing out, saying that there is a voice breakage, and maybe all of us can switch off that YouTube link if we are playing it parallelly on our local system. And also we can cut off the video in case the audio quality can be used for bandwidth purpose. That's also one possibility. Sir, can you check, sir, once? Yeah. Sir, there is one more question, sir. Here, maybe I can read out the question. This is related to, this is I think is, yeah. Related to shear forces, and since we are also having a large velocity gradient across a shock wave. Sir, you are okay, calling. Hello, sir, go ahead, sir. Oh, there is a power failure, sir, in your place. Okay. Oh, I see. Sir, there is one small question, almost, since we are also having a large velocity gradient across the shock wave, therefore we are getting a large value of shear force also. How to decide at what radius the shear force is having maximum value? This is, in a traditional sense, is looking at, this question is from Ravinder Singh.
Distance are so small that we are not looking at the shear at all. You know what the shear does is the rate of shear being high, it dissipates the energy and causes heat to get generated. And it is this heat which generates the temperature, high temperature. And therefore you are getting the high temperature in the shock wave is because of the dissipation. Therefore we don't really model the shear forces behind a shock wave. We presume that the dissipation effects in a shock wave take care of it. I think this is the answer. We are not looking at gradients because the shock is so thin, less than a micron or of the order of microns, that we are talking of molecules in that region, and we cannot really apply the equations which we use under continuum for modeling shear in a shock wave. This is the problem.
Yes, sir. Yes, sir. This is also related to the jump discontinuity that exists among all the properties in terms of, the variations in terms of density, pressure, temperature, and so on. So we have to look at that particular small, region of very sharp changes that do take place, and therefore the shear forces in a traditional sense of the continuum, and then that needs to be.
But we don't look at that very thin zone.
Yes, sir.
We presume that the shock is so thin that it is a discontinuity.
Yes, sir. Yes, sir.
We don't model it unless we go to Boltzmann equation and stuff like that, which is beyond the first level course for a shock.
Correct, sir.
I think.
Yes, sir. Yes, sir.
I think you carry on. I think the power may not come immediately.
Sure, sir. Sure. I'll see. Yes, sir.
Okay, sure.
Bye, sir.
Thank you.
Bye. Hello, participants. Sorry, Professor Ramamurthi had some power cut issue, and therefore he could not, really sort of continue with us. And that's a bit unfortunate. Anyway, he is also my teacher, and so in fact, I was telling sir to come here and then get connected. Anyway, let us try to see some other questions. Anything from participants? Please do feel free. I don't see any other serious chart question other than these 3-4 questions. Yeah. Any other chart question that nothing else is popping up? Maybe. Voice goes silent for some time, then it comes back in a very fast speed. Yes, I too experienced something like this. So I'm not sure. I think sir was depending on possibly on the UPS, and therefore there was some issue there. There was a power cut locally, and then any other chat questions that are popping up? I can take a look. So I don't see any question beyond this. Related to sonography, I think Professor has answered, and related to, I think the shear force related issue, sir has answered already, and the discussion is one of jump discontinuity that exists across a shock wave, and the changes that do take place within that small micrometer kind of a thin zone is something that the continuum laws will not be able to sort of take that. It's more like a step discontinuity kind of thing. In the left limit, you have certain bunch of in a mathematical sense, when you do at x equal to some location x equal to 0 or something, at that position you do have at 0 plus and 0 minus, the two values are very different. In that sense, one has to look at that particular small thin region of jump discontinuity very carefully, and then the traditional continuum laws will not be able to address that. So any other questions? Otherwise we can sort of temperature changes continuously during reaction, but this is a jump discontinuity. A blast wave is a decaying shock wave as it progresses. As you know, I think Ravinder Singh is asking a question. Temperature changes continuously during the reaction, but we take only one value. Which one value you are referring? So it's I mean, the temperature changes typically when you look at additionally, if there are issues related to, I mean, when we talk about shockwave propagation, we are essentially looking at the blast load initially, and then of course there is a huge influence in terms of the temperature changes also. And but the small thin zone that we are referring, okay, the Arrhenius equation is what you are referring. Okay, we'll ask professor to address this. I'm not sure what exactly is your concern. Maybe I'm not sure about the accurate response to your question related to in Arrhenius equation. What is a complete question then, Ravinder Singh? In Arrhenius equation, temperature changes continuously during the reaction, but we take only one value. Yeah, I do not know the answer for this. I'll ask professor. Okay, any other questions which perhaps maybe one interesting thing that I saw in the YouTube, they had a nice plume coming out of this blast wave, and you can see the wide range of scales that are present within this that picture that I saw was a huge plume of uh, fireball kind of thing was coming out, and then you can see wide range of or wide spectrum of scales, spatiotemporal scales, and one can easily notice a wide range of length scales and time scales. When we say length scales and time scales, they essentially span over from which source it has come. So starting from some kind of integral scale eddies all the way to the dissipative scale eddies would be present. By looking at the plume dynamics, one will be able to easily decipher what is the size of the explosion. I'm sure those kind of calculations can be brought in easily from first principles based ideas related to straight away connecting it to the Reynolds number, the characteristic velocity scales and length scales involved in that system versus its relation to the corresponding scales of dissipation or corresponding scales of loss of energy that do take place in a certain time scale and length scale. And that relation typically sort of can be easily figured out in terms of, for example, the length scales of those small scale eddies could be thought in terms of integral scale times Reynolds number to the power of minus 3/4, and one can sort of correlate the size of the plume and the size of the detailed features present in the plume to the corresponding size and scale of the explosions also. It's possible. So Balaji, what is the standard procedure for the closure? Or because one or two questions only professor can address.
Yes, sir. Yeah, we can close the no issues. Sir.
Because there is no more chat discussion that I notice here.
No issues, sir. We can close and we will have a session. I mean, later on after 2 weeks or so.
Yeah. After 2 weeks or so, we can have
Yeah.
a separate session.
Sure, sure. You can give a
Okay.
concrete remark saying that if if they have any more questions, they can put it on the discussion forum and we can address them there.
Yeah. If there are any other questions related to this, the classes start by Professor Ramamurthi, please also identify the lecture number and the corresponding location of the video that you have a specific question. And that will help us to sort of go back and then see the specifics, because sir has started this course and he will be knowing the specifics associated with the concern behind your question, and therefore it's possible that that specific part it will be nice if only sir is addressing rather than me trying to figure out what it is and so on. Also, anything to do with assignments, etc., also you can sort of raise your concern and we can look into that. Thank you. Otherwise, thank you for all your participation. We could see about 10 to 12 active participants, maybe a lot many maybe watching live. And thank you for your support.